So now we'll get into some results about vectors. So we've got a zero vector. And it doesn't matter whether we're in 2 dimensions, 3 dimensions, or even higher. The zero vector is just a vector where all the components are 0. In this case, this is really the unique vector that has no direction. Its magnitude is 0, and it doesn't even have a direction. It doesn't point in any particular direction because its magnitude is 0. We can do some algebraic operations on vectors. So if u and v are 2 vectors here, and c is a scalar, so c is just some real number, then we can, first of all, we can check whether 2 vectors are equal by just comparing their components. If their components are all the same, then the 2 vectors are equal. What about algebraic operations on the vectors? Well, we can add 2 vectors together. I can take u and add it to v. And the way I do that is I just add their corresponding components. So this is algebraically how we would add 2 vectors. We just add the x components, the y components, and the z components. The way we can think about this visually is as follows. So we'll just sketch it down here. If I had a vector u, and I have another vector v, and we'll put little vector symbols on top of them, and I want to add them together. Notice I haven't attached them to the same point because vectors are free to be attached anywhere. So I've got these 2 vectors, or these 2 arrows, and I want to add them together. The way I can add them together is I can do it in one of 2 ways. I can grab one of the vectors and just attach it to the tip of the other one. And I'm going to move our label so it's up top now. And then what I've done is I've really created from the tail of the first vector to the tip of the second vector, I can now construct a vector that goes from one to the other, and that is the sum of the original 2 vectors. And you can see now why this definition makes sense. If I'm going to define it in terms of this picture, then it really means that how did I get from the tail of the sum vector, or the yellow vector, to the tip? Well, I just moved along the x direction. I moved whatever distance u took me in the x direction plus whatever distance v took me in the x direction. And similarly for the y direction. To get from the tail of the yellow vector to the tip of the yellow vector, I just went however far up u took me plus however far up v took me. And so that's the pictorial representation of the corresponding sum of 2 vectors that we gave algebraically as just adding the components together. This is known as the triangle law for adding 2 vectors. There's another way to think about adding 2 vectors, and again what I'm going to do is I'm just going to copy and paste. So we'll use these same 2 vectors, paste. The other way I can think about this is I'll just take the 2 vectors and I'll imagine that they both start at the same point. So they have the same tail point. And then what I'll do is I'll just copy one of the vectors, add it to the tip of the other, and vice versa. So I'm making 2 copies of each vector. And the 2 copies were, you can see them there, they're really the same vector. I took a couple of copies of v, a couple of copies of u, and I made a parallelogram out of them. Now the sum of the 2 vectors is just the diagonal of this parallelogram. So that's u plus v. And that's called the parallelogram law for adding 2 vectors. So you can think of the addition pictorially in either of these 2 ways, by moving one of the vectors to the tip of the other one and looking at the sum as just tracing along one vector and then along the other one to get from some point, which is the tail of the first vector, to the tip of the second, or you can construct a parallelogram made up of the 2 vectors and get the diagonal of that parallelogram is the sum of them. Scalar multiplication is another operation we can do to a vector. So we can take a vector and we can multiply it by a real number, in this case our scalar c. And what this is the following. Maybe I'll get a picture for that as well. if this is our vector u, then I'm imagining here that c is bigger than 1, then c times u would be some scaled version of it. If c is positive but less than 1, then it would shrink the vector. If c is negative, then it just points in the other direction. We'll get to that in the next bit of notes here. So how does length change under scalar multiplication? Well, under the notes here, part A, it says that if you scalar multiply a vector by c, then the magnitude of that scaled vector is just the magnitude of the scalar that you multiplied by times the length of the original vector. And a couple more bits of terminology is we say that two vectors have the same direction if one is a scalar multiple of the other where the scalar is positive. So for example, if this is our vector u, then our vector v, if it's in the same direction, it's some scalar times u, where in this case c, not only is it positive, it's bigger than 2. Now they have opposite directions if one of the vectors is some scalar times the other vector. And in this case, that scalar has to be negative. So this would be, for example, if that was vector u, then vector negative u would just point in the opposite direction. And these two would have the exact same length. They just have opposite direction. So we can change the direction of a vector by multiplying it by a negative. We can change the length of a vector by multiplying it by some scalar not equal to 1. Lastly, because we can now do addition and scalar multiplication by numbers that are negative, we can do a difference. What is u minus v? So here it's not surprising that u minus v is just, you take u and you subtract each of the components by the corresponding component of v. What I want to get out of this, though, is the corresponding picture. So here the idea is we've got a vector u, we have a vector v, and we'd like to, much like we did for the addition up above, we'd like to come up with a visual for what is the difference of these two vectors. So the difference of them, again, we'll copy and paste. And now we want to take u minus v. Well, that's like taking u and adding minus v to it. So it's going to look like that. And therefore, the corresponding difference is this vector here, u minus v. So that's one way to think about it. It's just go along u and then attach negative v to the tip of that, go along negative v, and that gives you the vector from the tail of u to the tip of that vector where you've placed negative v. That's one way to think about the difference. The other way could be, well, suppose I don't want to think about negative v. Suppose I just want to think about u and v in terms of their original directions that they've been given. So what I'll do is I'll take u and v and I'll make them start from the same point. And now I want to envision, what does u minus v look like? Well, u minus v is the vector that goes from the tip of the vector v to the tip of the vector u. That's u minus v. You might say, well, how do I know that? Well, let's think about just walking our way around the triangle. If I start at this point here, and I go along v, and then add to that u minus v, then I get u minus v plus v, so that just gives me the vector u, which is exactly where I'm ending up here. I'm ending at the tip of the vector u. So that's another way to visualize the difference of two vectors. I can imagine them starting at the same point and then visualize the vector that goes from the tip of one to the tip of the other. And it depends which tip I go to, depends on which vector I'm subtracting from which one. So again, we can think of this as tip minus tail. It's the vector u minus the vector v. So I go to the tip of u minus the tip of v. Alright, so now we've got a way to add and subtract vectors, scalar multiply vectors, and also visualize those operations. One of the important things that we'll be able to do with vectors is to just strip off the magnitude of it and just make it a unit vector, so a vector of length 1. And this is really just when we're interested in the direction a vector is pointing in. So if I have a vector A, I can what we call normalize it, or make it of unit length, by just dividing by its length. So I take A, the vector A, and divide by its length. That's scalar multiplying by 1 over the length of the vector, and that gives me a unit vector. And it points in the same direction of A as A. A couple of unit vectors that are really important for us are going to be the standard basis vectors. So in 2 dimensions, our standard basis vectors are I and j, and we usually say I hat and j hat to designate them as vectors. The little hat symbol is used in place of the arrow symbol, just because these vectors have special status. What these vectors are, at least in 2 dimensions, they look like this. So we've got our x-axes, we've got our y-axes. So I hat is the unit vector, vector of length 1. That points in the I direction. And j hat is a vector of length 1 that points in the y direction. For any vector, we can now write it, instead of using the component form and angle brackets, we can write it in terms of linear combinations of the standard basis vectors. So instead of writing the vector A as A1, A2, I could write it as, well, it's A1 times the I hat vector plus A2 times the j hat vector. It's just another way we can write a vector instead of using the angle bracket notation. In 3 dimensions, we have I hat, j hat, and that third direction, the vector in the direction of the z-axis, positive z-axis, is given by k hat. And we can again write using the standard basis vectors, the corresponding vector with components a1, a2, and a3. Instead of an angle bracket notation, we could use this linear combination notation. So let's have a look at a few more examples. Suppose that u is the vector negative 2, 1, and v is the vector negative 2, negative 1. Is it true that u is equal to v? Are these the same vector? And the answer is no, because their y components are different, or their second component is different, so no. U is not equal to v, because in order to be equal, all the components have to be equal. Let's find the sum of u and v. So u plus v, that's going to be negative 2 plus negative 2, that's negative 4. 1 minus 1, that's 0. What is 2u? That is going to be negative 4 and 2. What is negative 3v? That is negative 3 times the components of v, so negative 3 times negative 2 is 6, and negative 3 times negative 1 is 3. And lastly, what is 2u minus 3v? So what's that linear combination? Well, we already worked out what 2u is. That's negative 4, 2. And we worked out what 3v is. That's 6, 3, or negative 3v is. And so I can just add these two together, and that gives me 2 and 5. How about the next example? This is in 3 dimensions now. If A is that vector and B is that vector, find the length of A plus B. First we'll find the sum of A and B. That is going to be negative 3, 6, and 5. So then the length of A plus B is given by the square root of negative 3 squared plus 6 squared plus 5 squared. Or in other words, it's the square root of 9 plus 36 plus 25. And so that's going to be 36 and 25 is 50, 61, plus 9 is 70, so this is going to have a value of root 70. What's the magnitude of negative 3a, well, we can use one of the results that says that's just the absolute value of the scalar times the length of the vector, because all we've done is by multiplying by negative 3, we just change the direction of the vector, we make it point in the opposite direction, and we scale it by a factor of 3. If we're only interested in the length, then all I care is that I've just scaled it by a factor of 3. So it's just 3 times whatever the length of the original vector a was. And the original vector a had length square root of 4 plus 9 plus 25. So that's 3 root 40. And how about 2a minus 3b? Well, that would be 2 times 2, 3, 5, minus 3 times negative 5, 3, 0. And that's going to be 4, 6, 10, plus negative 3 times negative 5 is 15, negative 9, and 0. So that is 4 plus 15 is 19, 6 minus 9 is negative 3, and 10 plus 0 is 10. And so there are the corresponding components of that vector. Let's have a look at the next example. Here we're getting used to the I hat, j hat, and k hat notation. So if A is negative 2 I hat, 3 j hat, 5 k hat, and B is negative 3 I hat, negative 3 j hat, and 5 k hat, let's write out the sum in terms of I hat, j hat, and k hat. So the difference, A minus B, not the sum. A minus B is given by, and all we do is just look at the corresponding components. Again, we could use the angle bracket notation, convert them both to angle brackets, do the difference, and then put it back in terms of I hat, j hat, k hat. But really, this is just saying those are the components. Whatever's sitting in front of the I hat is the first component, whatever's in front of the j hat is the middle component, whatever's in front of the k hat is the third or last component. And so I can just work on components much the same way as using the angle bracket notation. So I've got negative 2 minus minus 3. So that's negative 2 minus minus 3, which is 1. Maybe I'll write that down here. So that's just an I hat. And the second term is 3 minus minus 3. So that'll be 6 j hat. And the last one is 5 minus 5, or 0 k hat. And since there's a 0 in the k hat term, what that means is we could leave it off and just write the difference as I hat plus j hat. This is one of the reasons why it's nice to use the I hat, j hat, k hat notation, because if I was to write this in angle bracket notation, this would be 1, 6, 0. I'd have to use another component. Even though it was a 0 value, I'd still have to include it. I have to use that third component with a 0 in there. But using the I hat, j hat, k hat notation, or the standard basis vectors, I can leave off the components that are 0. I don't need to write them in there. And that's kind of nice. It saves the amount of writing we have to do. It eliminates us having to write zeros when we don't really need to worry about them if they are 0, if that component is 0. And so that's the benefit of using the standard basis vector notation. Alright, and now we'll finish up with our properties of vectors. Now all of these properties just follow from the definitions we've given for sums and scalar multiplications in this section. But these are some properties that we will be using time and time again when dealing with vectors. So the first one is that it doesn't matter whether you add u to v or v to u. Vector addition is commutative. You could do it in either order. U plus v is the same as v plus u. If you add the 0 vector to any vector, it doesn't change it. You just get the original vector back. Scalar multiplying by 0 produces the 0 vector. If you scalar multiply by a and b, that's the same as scalar multiplying by one of those values and then the other one. If you scalar multiply by the sum of two values, that's the same as scalar multiplying by, in this case, a, and then adding to that the scalar multiple of the vector u by b. So we say that this is the distributive property, and so we'll just make a note of that. This is the distributive property, or a distributive property. There is another distributive property. So this says that vector distributes across the sum of two scalars. We also have that a scalar can be distributed across the sum of two vectors. So this is another distributive property. So in this case it was the vector distributed across the sum of two scalars, whereas in the last one it's the scalar distributes across the sum of two vectors. Property F says that if you're adding three vectors together, it doesn't matter which ones you add together first. So I can add the first two or the last two, it doesn't make any difference. If I add a vector to its negation, then I get the zero vector, and if I scalar multiply by 1, I just get the vector back. So these are the properties of vector operations that we have, and we'll be using them time and time again. Alright, so that's been our basic introduction to vectors in 2 dimensions and 3 dimensions, and vector operations or arithmetic operations of addition, subtraction, and scalar multiplication. In the next 2 sections, we will introduce some more operations on vectors, namely the dot product and the cross product, and that'll help us explore a little bit more of the geometry of vectors in 3-dimensional space. Alright, thanks for watching, and we'll see you in the next lecture.